PreAP PreCalculus Notes section 4.1. We are at the conclusion of these notes, which is basically summarizing everything we've done in it. We started out this section with this function right here, and we tried to determine how many roots are there in this based upon the fundamental theorem of algebra. We tried to figure out how many of these roots are positive, how many of these roots are negative, how many of these roots are zero. We may not have actually done that for this function. And then how many of these roots are imaginary? We're going to put all that together and try to answer this question. Draw a table below that summarizes the possibilities of the types of roots of p of x. Then graph the function on the calculator and put a star beside the combination that is correct. All right. So first of all, how many roots does this have? This has 4 roots because of the fundamental theorem of algebra. We know this has 4 roots for sure. Possible number of positive roots. Well, how many sign changes do we have in this? Descartes' rule of signs. We have a sign change here and a sign change here, which means the possible number of positive roots is 2 or less than that by an even number, or it could be 0. Possible number of negative roots. To do this, we have to examine p of negative x. If you put a negative in and the exponent is even, it remains how it is. If the exponent is odd, it changes signs. So it's even, stays the same, odd changes sign. Even stays the same, odd changes sign. No variable. How many sign changes are here? 1, 2. There are 2 sign changes. Possible number of negative roots, 2 or 0. How many of these roots are 0? Well, we would say that none could be 0 because we have a constant term. We cannot factor an x out of this equation, so it's 0. Possible number of imaginary roots. Well, this is a 4th degree polynomial, so there could be 4, or 2, or none. We're going to put all this information in a table and look at different combinations. So my table, I'm going to have positive, negative, 0, and imaginary. Different rows. Those are the headers for the columns. I'm going to try to list every combination that I can based on the numbers that I have up here answering these questions. So positive roots, there could be 2. Negative, there could be 2. Now, 2 plus 2 is 4. If that happens, there can't be any 0 and there can't be an imaginary. We know that none of these could be 0 to begin with, so I'm just going to pre-fill this stuff out with zeros. Maybe there are 2 positive, no negative, but 2 imaginary. We've just listed all the combinations where there's 2 that are positive. Now let's go 0 that are positive, 2 that are negative. Then there has to be 2 that's imaginary. We could go 0 that's positive, 0 that's negative, and 4 that's imaginary. I think that we've listed every combination. Now, to determine which one is correct, the directions say, use your calculator to determine which of these are actually true. So I've already got this graphed. We can see that we have 2 negative roots and we have 2 positive roots. So our first possibility was the correct one, which we didn't know that. It just happened to be that way. It says put a star beside the right combination. There are 2 positive roots, 2 negative roots. So there are no imaginary and none that are 0. Let's check out another. Same directions, essentially. For each function below, use Descartes' rule of signs to help determine all the possible combinations of positive, negative, 0 imaginary roots that our function may have. Then graph the function on the calculator and put a star beside the one that works. So, sign changes, 1, 2, 3. I'm going to make a little table here. I'm making a table before I make my table. Positives, there could be 3 or 1 because there were 3 sign changes. F of negative x, if I'm putting it into a term that has x and it's an even exponent, it stays the same. If it's an odd exponent, that term changes signs. So the first term is odd exponent, so it changes sign. Next term is an even exponent, sign doesn't change. The next one is odd, the term changes sign. The next one's even, does not change sign. There are no sign changes here for f of negative x. So there are no negative roots. Are there any roots that are 0? There are, because we have no constant. Our GCF that we could factor out of this is x squared. That means that we know for sure there are 2 roots that are 0. So the graph is tangent to the x-axis at 0. That's what we know. And then as far as imaginary goes, big picture-wise, since this is the 5th root, there could be 4 or 2 or 0. Now we know it's not 4 right away because there are 2 of these that are 0. And 2 plus 4 is 6, which is more than this could actually have. So let's actually make our table now. We got positive, we got negative, we got 0, and we got imaginary. We're going to pre-fill in the 0 column because we know it has to have 2. I don't know how many of these combinations I'm going to have. There could be 3 positive, and if 2 are 0, that means these have to both be 0. There could be 2 zeros that are 0, which we know for sure. There could be 1 positive. That leaves 3 roots left, so there could be 2 that are 0, 2 that are negative, and 0 that are imaginary. We know that there are 2 zeros that are 0. We could have 1 that's positive, none negative, and 2 that's imaginary. And that's all we can do. Like, we can't do 2 and 3 because this column here has to always be even numbers. So unless I'm missing something super obvious, those are all the combinations. Let's look at the graph. Whoops, let's make this bigger. So we can see here, whoops, I just deleted that. I didn't want to do that. As we predicted, it is tangent to the x-axis at 0. There are 2 zeros there. We know it's even. We're thinking there's 2. This one here is a positive one. It doesn't change concavity. So we got 2 at 0. We got 1 positive. If I zoom out, this isn't coming back and touching this graph anyplace else. So that must mean that there's then 2 imaginary. Let's see if we had that combination written down. Yep, 1 positive, 2 zeros, and 2 imaginary. Let's check out P. How many sign changes? 1, 2, 3. So there are 3 or 1 positive real zeros. P of negative x, if the exponent is even, I leave it alone. If it's odd, I change the sign. Even, leave it alone. Odd, change the sign. Even, leave it alone. Odd, change the sign. Constant. There is 1 sign change in this, and that's from here to here. So we know for sure that there's 1 negative real root. Are there any that are 0? The answer is no, because it has a constant term. So imaginary, I can just put an I, sorry, got overzealous. We would normally say, well, there could be 4 or 2 or 0, but there can't be 4. Let's write this down. 4 or 2 or 0. There can't be 4 because we know one of them has to be negative. So all 4 of them can't be imaginary. So we're going to say there could be 2 or there could be 0. So let's make a table to summarize this and list combinations. We got positive, we got negative, we got 0, and we got imaginary. Now we know in the negative column it has to be 1. The other 3 could be positive. We also know this is 0 all the way through. You don't have to worry about that. So then this will be 0 because 3 plus 1 is 4. Once again, the fundamental theorem of algebra says this is a 4th degree polynomial, so there are 4 roots. We need these columns to have to be 4. We know there's 1 that's negative. Maybe there's 1 that's positive, and there are 2 that are imaginary. I don't think there's any other combinations. We can't change this column, we can't change this column. So it's 3 and 0 or 1 and 2. That's all we can do. Let's look at our graph as I stutter. P of x, we see we have 1 negative, 1 positive. If I zoom out, it doesn't appear to be any more. So it's 1 positive, 1 negative, 2 imaginary. All right, we got 2 more of these little fellas. Always make sure that these terms are in descending order. I haven't mentioned that for a while because they've always been that way, but they won't always be that way. How many sign changes? 1, 2. So as far as positives go, positive, real, 0, there's 2 or none. Q of negative x. When I plug this in, if the exponent is negative, I change the sign of the term. If it's positive, I leave it alone. So change the sign, I leave it alone. Change the sign, I leave it alone. There's 1 sign change here. So once again, we know there is 1 negative real 0. Are there any zeros that are 0 for this? There are not, because we have a constant term. So as far as imaginary goes, there could be only 2 or 0, because they always come in even pairs. The fundamental theorem of algebra says that there are 3 zeros, so there could be 2 or there could be 0. Put this in a table. I got my positives, my negatives, my zeros, and my imaginary. I know my negative one is 1. That is, can't be changed. So there could be 2 positive, and I know this one can't be changed either. This is 0 all the way down. Then there would be no imaginary. Or there could be no positive ones, and there could be 2 imaginary. There are no other combinations. Let's look at the graph of this. This was Q of x. And we can see there's 1 negative. That must mean the other 2 are imaginary. Starring the correct row. Boom. Last one. See if I can make my work a little more succinct here. Positive. If I can cut out some extra work. Negative, 0, and imaginary. So we got 1 sign change, 3 sign changes. So positive could be 3 or 0. This is probably better if I just write it up here like this. I like this better. Negative g of x, g of negative x, is going to be 3x to the fourth plus 2x cubed minus x squared minus 2x minus 5. One sign change. So this is 1, indisputable. There are no zeros because this has a constant. As far as imaginary goes, there could be 4, 2, or 0 because the degree of the polynomial is 4. Fundamental theorem of algebra says there are 4 zeros. But we've already used one of them here, so it can't be 4. And remember that the imaginary ones have to come in even pairs. So this column set and this column set, they're 1 and 0. This could be 3 or 0, which makes this, that's interesting, it makes this 0. I'm sorry, I made a mistake here. This is not 3 or 0. This is 3 or 1. There are 3 sign changes, so this is 3 or less than that by an even number, so it's 3 or 1. My apologies. So if that's 1, then there would be 2 imaginary. So we got 3 positive, 1 negative, no 0, no imaginary. 1 positive, 1 negative, 0 zeros, and 2 imaginary. If we look at our calculator, we graph this little fella, you will see that we have a negative and a positive. It's not changing concavity, so those don't have any weird multiplicities. 1 positive, 1 negative, and then 2 imaginary. All right, that finishes up this section. There's a lot of information in here, but you can see that once you understand the information, whether you do yet or not, I don't know, actually applying it doesn't actually take all that long. Please do the homework for 4.1.